formation in the Black Hills of South Dakota that geologists classify as a laccolith, a dome of igneous rock pushed upward from below by magmatic intrusion. It is roughly cylindrical. Its top is relatively flat compared to its sides, and its sides display a regular pattern of vertical striations running from the base to the summit, spaced at intervals that, when measured, appear to follow a consistent geometric pattern around the full circumference of the structure. The formation is called Bear Butte, and it rises approximately 400 feet above the surrounding plain. Geologists date its formation to approximately 50 million years ago, but if you look at Bear Butte without the geological explanation already placed in your mind, and then you look at a cross-section of a large tree trunk showing its vascular bundles, the structures that move water and nutrients through living wood, the resemblance is not subtle. The vertical striations of Bear Butte match the pattern of vascular bundles in a tree trunk with a specificity that goes beyond the kind of loose analogical thinking that usually produces alternative interpretations of geological features. The geometric regularity, the consistent spacing, the way the striations follow the curvature of the structure, these are properties that the laccolith explanation accounts for as coincidence. The tree hypothesis accounts for them as function. And Bear Butte is not unique. Formations sharing this specific combination of characteristics, a cylindrical or dome-like profile, vertical surface striations following a regular geometric pattern, a flat or fractured top, and isolation from surrounding mountain ranges, appear on every inhabited continent. Devil's Tower in Wyoming, which shares Bear Butte's geographic region, is perhaps the most photographed example. The Giant's Causeway in Northern Ireland, the organ pipe formations of the Drakensberg in South Africa, certain features of the basalt columns at Fingal's Cave in Scotland, the isolated buttes of Monument Valley, the mesas of the Atacama Desert in Chile, the flat-top mountains of Roraima in Venezuela. Across all of these formations, in varying degrees and with varying levels of preservation, the same combination of features appears. The specific combination of traits that characterizes a very large biological structure, rather than a geological one, can be seen by anyone willing to look, without allowing the interpretive framework of conventional geology to direct attention somewhere else. And I want to be precise about what this hypothesis is and what it is not, because the version of this idea circulating online is often so imprecise that it weakens the genuinely interesting question underneath it. The claim is not that all mountains are tree stumps. Mountains are clearly not all tree stumps. The Himalayas, the Alps, the Rockies, in their full extent, these represent tectonic and glacial processes that produce landforms qualitatively different from what the tree stump hypothesis describes. The hypothesis is narrower than that, much more specific. It proposes that certain categories of isolated, roughly cylindrical rock formations with particular surface features may represent the mineralized or solidified remains of organisms that, while living, were dramatically larger than any organism currently recognized in the biological record, and that those organisms were biological rather than geological in origin. Stated that precisely, the hypothesis is not something the geological literature can verify, at least not as it currently stands. And the reason is simple. The geological literature was not written to answer that question. It was written to describe formations inside a theoretical framework that assumes no biological process has ever produced structures at mountain scale. If that assumption is correct, then the question never arises. But if the assumption is wrong, or if the relevant biological processes operated in a period that predates what the geological record is currently understood to preserve, then this becomes a question the existing literature cannot answer, not because the answer was investigated and found to be negative, but because the question itself was never seriously investigated at all. That distinction matters. In fact, it matters more than almost anything else in this discussion, because the official scientific dismissal of the tree stump hypothesis consistently fails to make that distinction. The dismissal says these formations are laccolith intrusions, or columnar basalt formations, or erosional remnants of sedimentary sequences, and those explanations are internally consistent within the geological framework. But what the dismissal does not say, because it cannot say, is that the biological origin hypothesis has been tested by the methods that would actually distinguish between geological and biological origins, and then found to be false. The biological origin hypothesis has not been tested. It has been categorized as unnecessary to test because the geological explanations are already available and already sufficient within their own framework. Start with Devil's Tower, because Devil's Tower is the formation whose properties have been most extensively documented and whose features most clearly illustrate what the biological hypothesis would predict. Devil's Tower rises 867 feet above the Belle Fourche River in northeastern Wyoming. Its summit is roughly elliptical, approximately 1½ acres in area. Its sides are composed of columns of phonolite porphyry, an igneous rock arranged in vertical bundles that range from 6 to 8-sided in cross-section and vary in diameter from 6 to 13 feet. These columns run from the base of the formation to the summit, with a regularity that geologists attribute to the uniform contraction of cooling magma. The geological explanation for Devil's Tower's columns is the same one applied to the Giant's Causeway and to other columnar basalt formations across the world. Lava or magma cools at a uniform rate. As it contracts, tensile stress develops. That stress is relieved by cracking that propagates perpendicular to the cooling surface. The result is a pattern of polygonal columns. This explanation is physically coherent, and it works especially well for places like the Giant's Causeway, where basalt columns emerge from a clear volcanic context, and lava flows are visible in the surrounding stratigraphy. But Devil's Tower presents complications that the standard cooling explanation handles less cleanly. The formation is phonolite porphyry, not basalt, and that difference affects the predicted column geometry under the cooling model. The columns at Devil's Tower are significantly larger in diameter than columns that basalt formations typically produce under the standard cooling explanation, and the isolation of the formation from any obvious volcanic source or contemporaneous lava field in the surrounding region requires the laccolith explanation, which proposes that magma intruded into overlying sedimentary rock formed the dome shape under pressure, and was later exposed by erosion of the overlying material over millions of years. That explanation is not implausible. But really, the important point is this: it requires a very specific set of conditions, and those conditions have left no other clear trace in the geological record of the surrounding region. The biological hypothesis for Devil's Tower predicts a different set of properties: a large biological structure, specifically a tree trunk or root mass of enormous scale that was later mineralized or silicified, would be expected to show a roughly cylindrical or tapered profile, surface features reflecting the vascular and structural organization of the original living tissue, a composition reflecting the mineralization of organic material rather than the crystallization of igneous rock, and an internal structure consistent with the preservation of biological organization rather than the uniform crystalline structure of cooled magma. So, the real question is not which story sounds more familiar. The real question is which set of predicted properties the actual physical data from Devil's Tower most closely matches. The phonolite porphyry composition of Devil's Tower is not the composition the standard cooling model would most naturally predict for a laccolith, but it is also not the composition one would most naturally predict for the mineralization of organic material. Mineralized wood, documented extensively in the geological record as petrified wood, typically preserves the organic carbon structure of the original tissue in a silica matrix, producing a material that retains the structural organization of wood while replacing its chemistry. The composition of Devil's Tower is not silicified wood in the ordinary sense. But the relevant question is not whether Devil's Tower is exactly like known petrified wood. The real question is whether the process is capable of producing the formation's specific combination of features are more consistent with a geological explanation or a biological one. Given what is actually known about both categories of process, the silicon dioxide content of phonolite porphyry is approximately 50 to 60%, higher than most mafic igneous rocks, but lower than typical silicified organic material. The rest of the composition is primarily feldspars, nepheline, and minor mineral phases consistent with a magmatic origin. That compositional evidence favors the geological explanation over the simple silicified wood hypothesis. But the biological hypothesis does not require that the original material was wood in the contemporary sense. It requires only that the original material was biological in origin and that the mineralization process which converted it to rock was different in character from the simple silification seen in conventional petrified wood. And the specific mineralization pathway that would convert biological material on that scale into phonolite porphyry has never been investigated, for the straightforward reason that no investigator has considered the possibility worth investigating. Move from the compositional question to the structural question, because really, this is where the biological hypothesis makes its most specific and most verifiable predictions. A columnar formation produced by the cooling of igneous rock should show column boundaries that are purely geometric, determined by the stress field of the cooling process. The interiors of those columns should be compositionally uniform throughout. The boundaries between columns should be filled with the same or similar material as the interiors, and they should show no evidence of any structural distinction that would reflect the boundary between two distinct biological units. The arrangement of the columns should be driven by geometric packing, not by an organizational principle related to function. But a formation produced by the mineralization of a large biological structure would be expected to show something very different. It would show structural features reflecting the organization of the original biology. The column-like features would have internal organization consistent with the internal organization of the tissue they preserve. The boundaries between those column-like features would reflect the original boundaries between distinct biological units, and those boundaries might show compositional or structural properties different from the interiors of the units. The arrangement of the column-like features would follow a pattern, reflecting the functional organization of the original organism. And here is where the problem becomes impossible to ignore. The actual structural data from Devil's Tower and comparable formations has not been collected with the question of biological versus geological origin in mind. Geological surveys have characterized these formations inside the geological framework, and they have produced data consistent with the geological interpretation, but they have not attempted to test whether that same data is also consistent with a biological interpretation. That is not proof that the biological reading fails. But really, the point is sharper than that. It is a gap in the investigation itself. The root question is the one raised from the very beginning. If these formations represent the above-ground portions of enormous biological structures, then what would the below-ground portions look like? The roots of any large tree extend to depths that reflect the structural and nutritional requirements of the biomass above ground. For a tree large enough to leave a stump several hundred feet in diameter and several hundred feet in height, the root system would extend to depths far beyond any mine shaft currently operating on Earth. The deepest mine shafts on Earth, the gold mines of the Witwatersrand Basin in South Africa, reach depths of approximately 2.5 miles. But the roots of a tree whose trunk had the dimensions of Devil's Tower would, by the scaling relationships observed in living trees, extend to depths of 10 to 30 miles into the upper mantle of the Earth. At those depths, roots would have encountered pressures, temperatures, and chemical environments entirely unlike anything known in contemporary tree root systems. Any biological structures capable of functioning there would have to be fundamentally different from anything in the living biological record. That is not evidence that such structures could not have existed. It is simply a statement of how radically different the organism would need to be. And that matters, because the geological features that might be interpreted as mineralized root systems of enormous ancient trees are already mapped under other names. Networks of linear features, dikes and sills, vein systems penetrating the deeper crust beneath mountain formations. Mining exploration records document these mineral-filled fracture networks extensively because they host economically valuable deposits. Geologists explain them through tectonic stress and hydrothermal fluid circulation. But some of those patterns show the same branching hierarchical organization that characterizes biological root systems. The branching mineral vein systems that miners encounter in deep exploration, a primary vein surrounded by secondary veins, surrounded by tertiary veins, follow the same geometric logic that governs root architecture in plants. Now, the identity of mathematical principles does not prove identity of origin. That would be going too far. But it absolutely raises the question of whether some geological features mapped as hydrothermal vein systems could instead be the mineralized remains of biological root systems on a scale never before considered. Then comes the timing problem, and there is no honest way around it. The official geological timeline places the formation of Devil's Tower and comparable formations tens of millions of years in the past, in periods that predate any organism recognizable as a tree at that scale in the biological record. If those dates are correct, then the biological hypothesis requires one of two things. Either organisms of this scale existed far earlier than the fossil record suggests, or the geological dating methods are wrong in ways standard analysis has not detected. The fossil record of early land plants extends back approximately 470 million years, with trees appearing approximately 385 million years ago in the Devonian period. The trees of the Carboniferous period included organisms like Lepidodendron that reached heights of over 100 feet and trunk diameters of several feet, enormous by contemporary standards, but still far below the scale that the Stump hypothesis requires. So the question becomes whether organisms substantially larger than anything in the documented fossil record could have existed without leaving fossil evidence. And the uncomfortable truth is that the fossil record itself cannot answer that. The fossil record documents what has been preserved and what has been examined. It does not document everything that once existed. Preservation bias in the fossil record is already well understood. Hard parts preserve better than soft parts. Marine environments preserve better than terrestrial ones. Common organisms preserve more often than rare ones. An organism whose tissue was primarily biological without dense mineral reinforcement, and which lived in an elevated environment where rapid burial was unlikely, would have a low probability of leaving recognizable fossils through standard preservation pathways. The mineralization pathway is a separate issue entirely. Conventional petrified wood forms when organic material is replaced molecule by silica, carried in groundwater, preserving structure while replacing chemistry. But the proposal that enormous biological structures were mineralized into formations like Devil's Tower requires a process different in scale, time scale, and perhaps even chemical pathway from conventional petrification. Such a process has not been described. But really, the absence of a described mechanism is not the same thing as impossibility. The organic origin of sedimentary limestone and coal is not disputed. Limestone is largely the mineralized remains of marine organisms, and coal is the compressed carbonized remains of Carboniferous forest material. In both cases, biological material became rock through processes, and the geological record clearly documents, even where the precise chemistry is not completely settled. So the suggestion that similar transitions could have converted biological material on mountain scale into the rock formations now observed is not categorically different from the biology to rock transitions that geology already accepts. It is only larger, stranger, far more disruptive to the present framework. Then there is the economic history of mining around the world's great isolated rock formations. A thread of evidence the geological literature has documented without following the inference it might support. Mineral deposits found concentrated around and within the base structures of formations like Devil's Tower, and more generally, around isolated rock formations with the cylindrical stump profile, are often rich in silicon, in organic origin mineral complexes, and in elements associated with biological processes. The specific distribution of mineral wealth in the deep crust, the concentration of gold, silver, copper, and other economically significant elements in vein systems penetrating deep below surface formations, follows patterns. Economic geologists have mapped extensively without asking whether those patterns reflect biological organization. The gold deposits of the Witwatersrand in South Africa are among the most intensively studied mineral systems on Earth, and their three-dimensional organization contains features that the standard fossil placer explanation accounts for only partially. The ancient sedimentary environment that supposedly concentrated the gold into specific stratigraphic horizons stretching across thousands of square miles would need to have operated at a geographic scale with few close parallels in documented geological history. The alternative possibility that the distribution of gold reflects the mineralized remains of biological organization operating at formation scale has not been examined. And if enormous biological root systems once penetrated to depths of tens of miles, then the resulting root channels, even after mineralization, would create pathways for fluid movement through the deep crust, fundamentally different from the fracture permeability of unmodified rock. The distribution of artesian springs, geothermal features, and deep groundwater resources around the base structures of isolated rock formations could reflect the subsurface drainage network of a mineralized root system. Hydrogeologists mapping groundwater systems in regions containing the cylindrical formations described here have documented anomalous spring distributions and unusual flow patterns that standard models explain through tectonic fracture systems. But the alternative explanation, biological root channel systems, has not been considered. That does not prove the biological model, but it does something more unsettling. It keeps reopening the same possibility from a different direction. Composition, structure, mineralization, vein systems, groundwater flow. Again and again, the official explanation remains internally coherent. But again and again, the question of biological origin is not answered. It is bypassed. The cultural memory preserved in indigenous traditions around the world's great isolated rock formations is not geological evidence, and it cannot be treated as geological evidence. But that does not make it meaningless. What is significant is the consistency of that memory across cultures that had no contact with one another and developed independently in response to the same kinds of formations in their own landscapes. The Lakota people of the Northern Plains, whose relationship with Devil's Tower is preserved in oral tradition, and whose name for the formation, Matotipila, Bear Lodge, reflects a specific cultural understanding of the site, describe it in terms that repeatedly characterize it as a living or formerly living thing rather than as a purely geological mass. The same pattern appears elsewhere. Aboriginal Australian traditions, describing certain rock formations as the petrified remains of ancestral beings, the Wandjina and other figures of the Dreamtime, are usually interpreted as mythological anthropomorphization of natural landforms. But really, there is another way to read them. They can also be understood as cultural memory, not necessarily perfect memory, but memory nonetheless of the biological character of features that may once have been recognized as the remains of living organisms. The academic tendency to dismiss indigenous traditional knowledge as a source of information about natural history has already been criticized within anthropology for decades. And there is a reason for that criticism. Aboriginal oral traditions containing accurate information about sea level changes at the end of the last ice age, documented by Australian researchers in 2015, demonstrate that oral traditions can preserve accurate information about geological events over tens of thousands of years. That does not prove that traditions describing rock formations as the remains of living beings are historically literal, but it does mean those traditions cannot be brushed aside simply because they do not fit the language of academic geology. They may contain information the academic tradition discarded before it ever examined it carefully. Then there is the silica question, and this is where the scale of the hypothesis widens dramatically. Silicon dioxide is the most abundant compound in the Earth's crust and is present in virtually every rock type. The standard explanation attributes that distribution to primordial geological processes that formed the crust from the mantle, with the present pattern emerging through billions of years of geological cycling. But there is another fact that sits beside that explanation. Silica is also the primary mineral component of many biological structures, especially in marine organisms such as diatoms and radiolarians, and the global biological silica cycle is a recognized component of Earth's geochemical systems. If biological organisms of very large scale participated in the silicon cycle of the Earth's surface during a period that predates or falls outside the current fossil record, then their mineralization would have contributed substantially to the silica inventory of the crust. The proportion of crustal silica that is biologically derived versus primordially geological is not a question the present framework has seriously asked, because asking it would require a starting assumption the current geological framework simply does not make. And that is the pattern, again and again. Not direct refutation, not decisive disproof, silence created by prior assumptions. The formations that most clearly preserve the external morphological features of biological structures are not spread evenly across the geological landscape. They are concentrated in specific geographic regions, and those concentrations are not fully explained by standard models. The concentration of Devil's Tower-class formations in the northern Great Plains and the Black Hills, the concentration of similar formations in the southern African highveld, the occurrence of characteristic buttes in the Atacama and in the Venezuelan highlands. These concentrations either reflect something specific about the geological history of those regions that current models still do not fully capture, or they reflect something about the biology of whatever produced them. And this brings the investigation to its central claim. The hypothesis built here is not that conventional geological explanations are simply wrong. That would be too easy, and frankly, too careless. The conventional explanations are internally consistent. They account for the available data inside their own framework. But the real hypothesis is more unsettling than a direct contradiction. It is that the available data has never been collected with the biological question in mind. That the interpretive framework of conventional geology has guided observation and analysis in ways that would fail to detect biological origins, even if biological origins were present, and that a systematic examination of these formations, using analytical methods designed specifically to distinguish biological from geological origins, could produce results that the current literature is not equipped to predict. What would that examination require? It would require high-resolution internal structure analysis using techniques developed for petrified wood examination. It would require isotopic analysis of mineral phases to assess biological versus geological fractionation signatures. It would require systematic comparison of the geometric properties of these formations with biological structures at scales where those properties are already established. None of these analyses have been carried out, not because they failed, but because no researcher with institutional access has had institutional reason to carry them out. That is why this hypothesis falls into the category of questions academic institutions are not built to investigate comfortably. It crosses disciplinary boundaries, it challenges foundational assumptions, and it asks geology to test a possibility that the incentives of academic geology do not reward researchers for taking seriously. But the mountains are there, the formations are there, the striations are there, the cylindrical profiles are there. The isolated positions in the landscape are there, measurable, photographable, physically present, visible to anyone willing to approach them without letting the conventional explanation decide in advance what they are allowed to see. The question of what produced them is still open in one very specific sense. The physical record has not been asked to answer it in the terms the biological hypothesis requires. The physical record is patient. It has been waiting for the correct question for as long as these formations have stood above the plain. They are old. They are silent. They are made of something that was once something else. And the thing they once were remains a question the official framework has not permitted itself to ask. The roots went down. The trunk stood. The forest surrounding it grew in a world the present world has replaced without remembering. Mineralization came, slowly or quickly, by geological standards, and converted what was biological into what is now classified as geological, without any investigator standing there to observe the transition or describe it in terms the modern scientific framework would recognize. What remains now is the shape of what was there. And that shape is specific. It has been measured. It has been photographed from every angle. It has been described in geological surveys and entered into geological databases. The classification is geological, but the shape is the shape of something that grew. And that distinction is the heart of the entire investigation. The stumps are what we call mountains. The roots are what we call the deep crust. The canopy they held, the sky they filtered, the moisture they produced, that is the world we have forgotten to imagine. And the world they grew in is a world the official record of Earth's history has still not found a place for. Not because the evidence against it is clear, but because the evidence for it has never been collected by anyone willing to ask the question seriously enough to follow where it leads. If this idea made you stop and think, leave your view in the comments. And if you want more investigations like this, stay with the channel, like, and subscribe in your own time.